The linkage is subjected to a force of 2 kilonewton. You can see here there is a force of 2 kilonewton at the point C. Determine the angle theta for equilibrium. The spring is unstretched when theta is equal to 0. Okay. So we have to see what are the forces which will be responsible for the virtual work. One thing we can see that when we are going to give some displacement, okay, we can give the displacement to this link either in the clockwise or anti-clockwise direction. So we can see that if I draw the free body diagram here, we will have what forces? The reactions. This will be the reaction at A, this will be the horizontal reaction at A, and this will be the vertical reaction. Similarly, there will be the reactions at hinge. Okay, both are hinge supports, therefore reaction at D, that is the vertical reaction, as well as the horizontal reaction. But we can see that both A and D are fixed points, isn't it? So they won't be responsible for the virtual work because A and D won't get any displacement. But we can see that there will be a displacement of point C, okay, either in the upward direction. Okay, if we are giving an anti-clockwise direction to the link, okay, if we are giving an anti-clockwise rotation to this link, then this point C will get lifted upwards. Or if we are giving a clockwise rotation to this link, then the point C will move downwards. Okay, so in both cases, whether we are giving the rotation in the clockwise or anti-clockwise direction, we will get the virtual work done by this force, that is P equal to 2 kilonewton. Plus we can see that there is a spring attached. Okay, there is a spring attached. This B point will also get some displacement in the X direction, both in the X direction and Y direction, isn't it? This point B will move both in the X direction and Y direction. But we are interested in finding the virtual work, and the force which will be responsible for the virtual work at point B will be the spring force. Therefore, we are interested only in the X coordinate of the point B. While as at the point C, we are interested in the Y coordinate because X displacement will also occur. C point will also get displaced in the X direction, but the force will be perpendicular. Therefore, there won't be any virtual work. Now, one thing to note here is that the spring is unstretched when theta is equal to 0. Currently, we are having theta. When will be theta 0? What should be the shape of the link that time? The link that time will be in this position, isn't it? This means theta is equal to 0 because theta is measured from here. Okay. When theta is equal to 0, then the spring will assume some position like this. This will be the position of the spring. Now, currently, what is the extension in the spring? Can you tell me what is the extension in the spring currently? Obviously, this distance will be the extension in the spring, isn't it? This is the undeformed state. This is the deformed state. Okay, this is the deformed length, that is L. This here is L0. So L minus L0 will give us the extension. Okay, so this distance from here to here is actually the extension in the spring. Okay, it is the extension in the spring. So we can also see how will this system look like after giving certain displacement to any of the links. See, this initial position is shown by the black color, and the final position is shown by this red color. Okay, and what I have currently assumed, the link has been given the angular displacement in which direction? In the anti-clockwise direction. Obviously, the points have lifted up. So if this was point C, actually, this will be the point C dash, and we are interested in the vertical displacement of this point C. Therefore, this will be equal to what? Delta YC. Okay, this will be equal to delta YC. And we are also interested in this displacement of the point. This was B. Okay. This is delta XB. Okay, so this will be the displacement of the spring. One thing to note is that this spring will always remain horizontal because there is a roller attached here. Okay, you can see from the figure, there is a roller here. So if this links are moving in the clockwise and anti-clockwise direction, the link BC will either move upwards or it move downwards. Okay, with it will also move the spring upwards or downwards because there is a roller attached. Therefore, it is free to move in the upward and downward direction. Okay, so therefore the spring will always remain horizontal. The spring will always remain horizontal. And the highest position of the link BC will be when theta is equal to what? When theta is equal to 0, obviously, then BC will be at its highest position. Okay. So I think this mechanism of the links is understood. Now we can find the virtual work. Okay. So the coordinates which we are interested in are the y coordinate of point C. So y coordinate of point C will be given by, we can see here that there is a right angle triangle. Let's say this is the length L. This is also equal to 0.6. Okay. If this is L, what should be the y coordinate here? It will be given by what? It will be given by this y coordinate will become the base of this right angled triangle. So this will be equal to L cos theta. And we can calculate the differential displacement. Therefore, we have to differentiate it. That is, it will be minus L sine theta delta theta. Okay, this is delta theta. So I can show here in this figure what is delta theta. I had forgot. Okay, so this will be the delta theta. That is, it will be the differential rotation. Okay, these are the differential linear displacements. This xb and this delta yc. This is the differential rotation. So this will be delta theta. So it can be shown on the FBD. The reactions won't do any work. We have seen it does not undergo any displacement. Now we are interested in which coordinate? This B coordinate, because B undergoes the displacement in the direction of force. Okay, B undergoes the displacement in the direction of force. Therefore, we will be interested in finding the x coordinate of B. So what should be the x coordinate of B? It will be L sine theta. Okay, so actually we are measuring this displacement from what? We can choose any fixed point to be the origin of our coordinate system. So this is the origin of the coordinate system. All the distances are measured from this axis, reference axis. This was point B here. Okay, so its differential displacement will be L cos theta and delta theta. So these are the coordinates which we are interested in. Okay. No need to find the x coordinate of C and y coordinate of B because there won't be any virtual work. Therefore, there is no need. Now we can simply apply which equation? And currently, if I want to show the free body diagram, the spring force will act in which direction? Positive x-axis or negative? It will act in the negative x-axis. Why? Because currently it is in the stretched position. We had seen that this was the unstretched position. From here to here, it was undeformed. There is some stretch in this direction. In the displacement is in the positive x direction. The restoring force of the spring will be in this direction. So this will be the restoring force of the spring. Okay. So don't say that it is in the direction of the linear displacement. We have to see actually in which direction is the spring force. Don't confuse it with the differential displacement. Okay, differential displacement is an imaginary displacement. Okay, the actual extension of the spring is in the x direction. Therefore, the spring force will be in the negative x direction. Okay, so this will be the spring force. Okay, I can again show here. This is the spring force. And this was the weight or the force which was responsible for the displacement. So now we can find out the virtual work. So delta U due to this point load and the virtual work due to the spring force. This has to be 0. So we can see that the work done by this P force, that will be, since P is acting vertically downwards and our imaginary displacement or the virtual displacement is upwards, therefore this work will be negative work. P is downwards and differential displacement is upwards, therefore. What about the spring work? Spring is acting, the spring force is acting in the negative x direction, and the differential displacement is also in the, here we have to see the differential displacement. Okay, both the displacements are in the, both the spring force and the differential displacement are in the same direction, therefore the work done will be, that is spring force multiplied by what? The differential displacement in the x direction. So we can write that this is minus P. What was delta yc equal to? So I don't need to take the minus here because I have already taken the sign of the work. Therefore, it will be L sine theta delta theta. And what is spring force equal to? Spring force is equal to the spring constant multiplied by the extension in the spring. What was the extension in the spring? What was the extension in the spring? I had told you that this from here to here, this is the extension in the spring. And naturally, this extension coincides with what? This extension coincides with the x coordinate of the point B, isn't it? X coordinate of point B and the extension in the spring are same. Okay, xb is also equal to L sine theta, and this is also the extension in the spring. Okay, so we can say that this is kx, and the extension in the spring is equal to, it was equal to what? L sine theta. And what was the differential displacement in the this delta xb? It was L cos theta delta theta. So we can write that as spring force is equal to kx, that will also be equal to extension in the spring, that is equal to k L sine theta. So this differential displacement is what? L. This has to be 0. From here we can get that minus P L sine theta plus K L square sine theta cos theta, and this will be delta theta, so this has to be equal to 0. So delta theta can't be equal to 0. So this term in the brackets will be equal to 0. Therefore, we will get that KL square sine theta cos theta this has to be equal to what? PL sine theta. So what was asked in the question? We had to find theta, isn't it? Okay. Determine the angle theta for equilibrium. Therefore, we have to find the theta. We can see that sine and sine will cancel out. L, we'll have KL cos theta, that will be equal to what? P. From here we will get that cos theta is equal to P by KL. The load was how much? 2 kilonewton. Spring constant was what? 15. What's L? Length of each link. So from here find the value of theta. 2 by? Don't you have calculator with you? So let's see one more question. If the box has a mass of 10 kg, determine the couple moment m needed to maintain the equilibrium when theta is equal to 60. Okay, it's quite simple question. Again, the points B and D are hinged. Therefore, in the free body diagram shown here, there will be the reactions, but they won't be creating any virtual work. And we can see that this moment has been shown in the anti-clockwise direction. Let's assume the differential displacement. Although it's a solved problem in the book, he has assumed the differential displacement in the same direction of the moment. Fine. So we can see that this is the initial position of the link, and after some differential displacement, after displacing it by delta theta, okay, angular rotation of delta theta, this link will obviously move upwards. Okay, AC move upwards when the anti-clockwise rotation is given, and it will move downwards when the clockwise rotation is given. So here, the forces which will be responsible for the virtual work will be, there will be the change in center of gravity of the weight. Okay, the location of the center of gravity. This was the initial position of the center of gravity. And now after some displacement, the center of gravity has moved upwards because the link AC has moved upwards. And that differential displacement has been shown by delta YE. Therefore, he has taken this to be point E, okay, A, B, C, D, and E. So this weight will be responsible for the virtual work, and this virtual work should be positive or negative? It will be negative because load is downwards and the displacement is upwards. By how much amount there is the differential displacement, that is delta YE. Therefore, we are interested in finding the Y coordinate of the point E to calculate this differential displacement. What other force or couple will be responsible for the virtual work? These masses are to be neglected because it's mentioned in the question, neglect the mass of the members. Therefore, only thing that will be responsible for the virtual work apart from this center of gravity will be this moment. Okay, we had seen the formula when there is a moment which causes some rotation delta theta, the moment will be equal to m delta theta. And if the moment and the displacement are in the same direction, then they will be treated as positive. The virtual work will be treated as positive. So here, since moment is anti-clockwise and the differential displacement is also in the anti-clockwise direction, this virtual work due to this moment will be positive, and the virtual work due to this weight will be negative. Obviously, their summation should be 0. It is quite obvious that if one is positive, then other has to be negative. Only then they can cancel out. So we are interested in finding the coordinate of the point E. So therefore, we have to fix the system, the origin of the coordinate system. This will be the reference x-axis, and this will be the reference y-axis. There isn't any need to find out where this moment is acting because it is a couple of moment is a free vector. Okay, there isn't any need of finding the coordinate of the point where m is acting because it can act at any point. So the coordinate of E will be equal to, that is, this coordinate will be equal to how much? If we can see that this will give us what? The displacement in which direction? Sorry, this will give us what? The y coordinate of A, isn't it? This will give us the y coordinate of A. In fact, even the y coordinate of C and the y coordinate of this point here. Okay, y coordinate of this point. But the center of gravity is at some distance from this height. You can see that this is the height. Okay, this right angle triangle will give us the height of this point A. Okay, but the point E is at what distance? At some distance from the point A, and that has been denoted by what? B. There is no need to find the B because after differentiating, this will get 0. Okay, because this distance B, okay, the distance of the center of gravity from the link AC will not depend upon the change in the rotation, isn't it? Can you figure it out? Okay, the distance B, that is from the link AC to the point E, will be independent of the rotation. Therefore, when we are going to differentiate it, the change in this length will be equal to 0. Okay. So how much will be this coordinate here? If this is a right angle triangle, then this will be 0.45. This y coordinate will be equal to 0.45 sine theta. Okay. But this is the y coordinate of point A. Actually, we are interested in finding the y coordinate of point B. Therefore, there will be some distance from the A to E, which has been assumed to be this B. Okay. Therefore, we have to add this distance as well. Okay. And now we can see that after differentiating it, it will be equal to what? Cos theta plus the differential will be 0. Therefore, it won't change with the angular rotation. Therefore, we can write that delta YE is equal to 0.45 cos theta delta theta. Now, principle of virtual work. There will be one virtual work due to the moment plus the virtual work due to what? Due to this weight. Now the applied moment is equal to, this has to be 0. Applied moment is m, and the differential displacement was what? Differential rotation in this case. Okay, it is equal to what? Delta theta. It is equal to delta theta. Here it has been shown. So I might have skipped the location of the delta theta in the previous questions. I want just to show you. For example, we had done this question. Okay, this was what? This was theta. Okay, so if this was theta, what would have been the change here? Okay, we can also show in this terms. Okay, although this now won't be equal to delta theta, but it will be equal to okay 90 minus theta, isn't it? This would be 90 minus theta. Then this would have been, this change would have been equal to what? So actually this would have been 90 minus theta. Then this change would have been equal to what? Delta of 90 minus theta. Okay, so we can also show it. What was this? Delta YE, isn't it? This was 0.45 cos of delta theta. Okay, so virtual work will be equal to delta U by of weight and delta U of moment. So this weight was acting in which direction? Downwards, and the displacement is in the upward direction. Therefore, this work has to be negative. Plus, moment is in the anti-clockwise direction, and the rotation is also assumed to be in the anti-clockwise direction. So this will be equal to 0. So from here we get that minus W, this is 0.45 cos theta delta theta plus m delta theta. This will be equal to 0. What's the weight? Okay, 10 kg. Therefore, it will be minus 10 into 9.81 into 0.45 cos. At what angle we have to find it? Okay, to maintain the equilibrium at 60 degree. Okay, so at different angles we will need different moments to maintain the equilibrium. Okay, so this moment will not be for the equilibrium at every position. So it is for a particular value of theta. Okay, So can you say that whether if this block is moving in the right direction, you can see that the moment the weight will be increasing, isn't it? Okay. If the block is moving in the right direction, that is if theta is decreasing. When theta will decrease, AC will move downwards and the block will move towards right. Then the moment created by the weight will be more. Okay. Then the moment which we have to apply to keep this block in equilibrium will be more. Now, as we are moving towards the theta equal to 90, the block is shifting towards left. Okay, because the AC is rising, the block will be shifting towards left. We will require less moment to keep it in equilibrium. Okay, so it will vary at different angles. So cos of 60 plus m delta theta is equal to 0. So delta theta can't be 0. Therefore, we can see that cos 60 is 1 by 2. This will be equal to minus m, because delta theta from here it was also multiplied with delta theta. Delta theta can't be equal to 0, therefore these two terms have to be same, which implies moment should be equal to what? 22.0, and its unit will be Newton meter.
There is a mechanism shown in this figure which consists of two links AB and BC, and in between these links there is a spring attached that is denoted by DE. There is also a mass, okay, a weight, a cylinder whose weight is equal to 50 pounds. Determine the angle theta for the equilibrium if the spring has an unstretched length of 2 feet. So one thing we can see that the spring is unstretched when theta is equal to 0. Okay, so you can see that this is the angle theta. When theta will be equal to 0, the links AB and BC will be completely horizontal. Therefore, we can assume that the scenario at theta is equal to 0, this roller C will be here. And we can see that this link BC will be this. Okay, this can be the position of the link BC, and this here can be the position of the link AB. So actually this is A, and this point is B, and this is C. So this is the condition of the system when theta is equal to 0. Also you can see that between A and B there is a point D, and between B and C there is a point E. What is connected between these 2 points is a spring. So we can see that when theta is equal to 0, the spring is unstretched and its length is equal to 2 feet. Okay, this is the stretch in the spring. I mean to say this is the natural length or the undeformed length of the spring, okay, when it is not loaded. After that, you can see that there has been a load applied at the point B in the form of a cylinder whose weight is equal to 50 pounds. So this creates what? This load is responsible for the mechanism to attain this final equilibrium position. Okay, you can see that this is the equilibrium position. So what we have to determine? We have to determine the angle theta for the equilibrium. Okay, we have to determine what is the angle theta for the equilibrium. So if we see, first of all, there is a hinge support at A. Therefore, we will get two reactions, AX and AY, and another support at C is a roller support. Therefore, we will get only the vertical reaction. There won't be any horizontal reaction. Now we can see that the point A doesn't get displaced. Therefore, the work done or the virtual work done on the account of these two reactions will be 0. But what can we see here? We have given some displacement or the virtual displacement in the x direction. Okay, the roller is moving towards left side. Okay, we can give the displacement to the roller either in the right direction or in the left direction. Currently, as per the book, this roller has been given the displacement in the negative x direction, that is towards left. So if this was the initial position of the point C, the final position of the point C will be this C dash. So what will happen, since this roller is moving in the left direction, this point E also shifts towards left. Okay, it's quite obvious that this point E will attain this final position, which can be denoted by E dash. And this link AB is hinged at A, therefore it is free to rotate about this hinge, and this, on the account of this rotation, okay, you can see that on the account of this rotation, if this is moving in the anti-clockwise direction, okay, this CE is moving in the anti-clockwise direction, okay, it's moving in the anti-clockwise direction, this link AD should move in the clockwise direction. Okay, this should move in the clockwise direction. So we can see that this point D is the initial position of the D, and this is the final position of D, okay, which is denoted by D dash. Therefore, there has been a virtual displacement of delta XD and a virtual displacement of delta XC on the account of these spring forces, okay. So one thing again, we can see that the spring is in compression, okay, the spring is in compression, because when theta was equal to 0, the points D and E will be farthest away from each other when theta is equal to 0. When at this position, okay, at this position shown here, you can see that the points D and E have come closer to each other. Therefore, the distance between D and E has reduced, which means that the length of the spring is less than 2 feet. Okay, the length of the spring will be less than 2 feet. Hence, we can say that in this case, the spring is compressed. In this position, spring is in compression. Okay, the maximum length or the original length will be when theta is equal to 0, then the spring is at its undeformed position. But at this given equilibrium position, you can see that the points D and E are closer to each other than what they were at theta is equal to 0. Therefore, we can see that this spring has undergone compression. And that compression can be given by, you can see that the compression in the spring. Now here, the final length is smaller than the original length. Therefore, we can say that the compression will be undeformed length or unstretched length minus the final length of the spring. Okay, this will give us the compression, which we can denote by X. So if we look at the unstretched length, that was equal to 2 feet. Okay, this was equal to 2 feet. And if we look at the current length of the spring, we can see that the current length of the spring is, this is the length of the spring. So from this triangle, okay, if we look here, there will be a triangle, this triangle, okay, DBE, okay, DEB. This is DE and this is point B. This angle will also be equal to theta and this angle will also be equal to theta. We can see that this distance, that is, this distance will be equal to, I can name another point in between them. Let's say that F. So DF will be equal to 1 cos theta, and FE will also be equal to 1 cos theta. Therefore, this total distance will be equal to 2 cos theta. Therefore, this DE is also the length of the spring in this position. Therefore, we can say that the compression is equal to 2 minus, that is undeformed length or the unstretched length minus this length at this instant, okay? Because the final length is less than the initial length, therefore this denotes the compression. Okay, this is the compression in the spring, and correspondingly the spring force will be equal to K into X. X is either compression or extension. In this case, it is the compression in the spring. Therefore, restoring force will be equal to K is given as 200. This will be equal to 200 multiplied by X is equal to 2 minus 2 cos theta. So this will be equal to 400 minus 400 cos theta. Okay, so this is the spring force. Again, see that in this diagram, the spring force has been shown in two directions. Okay, so it's obvious that the spring force will be shown. Now, assuming that this end is fixed and this is the spring and it is acted upon by some external force in this direction, which is leading to the compression in the spring. Therefore, this end is fixed. Therefore, the restoring force will be only shown in this direction. Okay, this will be the restoring force. But see here in this case, D isn't fixed. Okay, the spring can extend or compress, okay, along the D as well as along the point E. Okay, that is in both directions the spring can, okay, at the both ends, okay, at the both ends of the spring can go extension or compression. Therefore, the restoring force will act at both ends. In this case, if it is fixed at one end, therefore the restoring force will be shown in only one direction. But these points are not fixed. The spring force will be shown in both these directions. Okay, and obviously the spring force here at the point E will be shown towards the positive x-axis, and at the D it will be shown towards the negative x-axis, because the tendency of the spring is to get extended because it is in compression. Therefore, this will be the restoring force here, and this will be the restoring force here, so that the restoring force creates an extension of the spring because it is in compression. Okay, so finally we can see that the virtual work will be done due to three forces. One is this 50-pound force, okay, and the virtual displacement corresponding to this 50-pound force has been denoted by delta YB. Similarly, you can see that this point E has shifted from right to left. Okay, so delta XE is the virtual displacement, and you can see that the work done by the spring force at point E will be negative because spring force is in the positive x direction and the displacement is in the negative x direction. Similarly, here you can see that the displacement of the point D is from right to left. Okay, this was the initial position and this is the final position of D. So it has undergone a displacement, a virtual displacement, which has been shown by delta xt. Okay, these are not the real displacements, these are the virtual displacements. Therefore, this has been shown by delta xt. And here you can see that the spring force and delta xt are in the same direction. Therefore, the virtual work done by the spring force at D will be positive. Okay, so we have identified all the forces which are responsible for the virtual work. See, these reactions won't be involved in the virtual work because point A is fixed, and here C is in the vertical direction and the displacement is in the horizontal direction. Therefore, there won't be any virtual work due to these reactions. Now, writing the principle of the virtual work, we can see that delta U will be equal to work done by the force at D plus the virtual work done by the force at E plus the work done by the virtual work done by the force at B. Okay, these are the three virtual works. Also, one can note, okay, we can also write their formulae. So the virtual work done at D will be equal to spring forces in the negative x direction and the displacement is also in the negative x direction. Therefore, we can see that spring force multiplied by delta xt plus here in the case of point E, the spring force was in the positive x direction, while as the displacement was in the negative x direction. Therefore, the work done here will be negative. The virtual work will be negative. Therefore, it is equal to delta S Fs into delta Xc. At last, the work done by this 50-pound force, that will be equal to both these forces and the displacement due to this load are in the downward direction. Therefore, this load will be shown by P. Okay, or we can directly write that it is equal to 50 pound multiplied by the virtual displacement of the point B, that is in the y direction. Therefore, delta YB. So this has to be equal to 0 from the principle of virtual work. Now we are interested in these few coordinates. Okay, we can see that we have to calculate the differential displacement of point D in the x direction. Therefore, we need the x coordinate of D. We also need the x coordinate of E, of point E, and we also need the y coordinate of point B. So we can fix our coordinate system, that is one of the fixed points has to be chosen as the origin of the Cartesian coordinate system. Therefore, this is to be fixed as the Cartesian coordinate system. So from here we can see that the distance of the the x coordinate of point D will be equal to so from this right angle triangle we can see that this distance of A to D along the x-axis, that will be equal to 1 cos theta. That will be equal to 1 cos theta. The distance of E from the origin, that is the point A, that will be equal to, we can see that this will be equal to so you can see that this distance from A to, let's suppose that this point is equal to, suppose AS will be equal to 2 cos theta. This distance will be equal to 2 cos theta because this length is equal to 2. This is equal to 2 cos theta, plus we have to add this distance as well. We have to add this distance. So from this right angle triangle, this distance will be equal to 1 cos theta. So from A to S, it is 2 cos theta, and from S to E, but along the x-axis, this distance is also equal to 1 cos theta. So we can see that this total distance is equal to 3 cos theta. And finally, the y coordinate of the point B, we can see that this y coordinate of point B is equal to, the y coordinate of the point B will be equal to this distance, this vertical distance, which will be equal to 2 sine theta. It will be equal to 2 sine theta, but it is in the downward direction. Therefore, this distance will be equal to minus 2 sine theta. The x coordinate and the x coordinate of the point E and D were in the towards the right of the coordinate origin. Therefore, they were positive, while as this distance y is in the downward direction. From the reference axis, it is in the downward direction. Therefore, we can treat this distance to be negative. So once we have located all these coordinates, what we can do is here find out the differential displacements or the virtual displacement. So delta xt here will be equal to minus sine theta delta theta delta xe will be equal to minus 3 sine theta delta theta, and the differential displacement or the virtual displacement of the point B in the vertical direction will be equal to minus 2 cos theta delta theta. Okay, so we already have considered the signs of the virtual works, therefore we can ignore these signs. Okay, we can only take their magnitudes. So we can write that from the principle of virtual work. Also, let's see fs. Okay, fs was equal to, we had seen that it was equal to 400 minus 400 cos theta. Okay, so now we can again write that delta u is equal to fs is 400 minus 400 cos theta delta xd, that is equal to sine theta delta theta, minus the spring force again, 400. I could have taken out this spring force, okay, as it is common, and in the brackets I will write that it is delta xt minus delta xe. So the spring force could have been taken common, therefore it was equal to 400, it was equal to 400 minus 400 cos theta, and in the brackets we will have xd minus xe, that is delta xd minus delta xe, that will be equal to sine of delta theta minus the magnitude, okay, only the magnitude sine of delta theta minus this 3 sine theta delta theta. And we are left with this 50, that is plus 50 into delta yb, that will be equal to only magnitude, that is 2 cos theta delta theta. So this has to be 0. So after simplifying it for the steps, we can see that delta u, this will be equal to 400 sine, okay, actually it was 400 sine theta delta theta. So this will be 400 sine theta delta theta and we have 400 into minus 400 into minus 3 sine theta delta theta, that will be equal to 1200 sine theta delta theta. Further, what we have here is minus 400 cos theta sine theta delta theta. And finally, what we have is minus 400 cos theta minus 3 sine theta delta theta, that will be plus 1200 sine theta cos theta delta theta. And there was one more force, that was this virtual work, 50 into 2, that will be 100 cos theta delta theta. So this has to be 0. So from here you can see that sine theta delta theta terms, okay, So we can take delta theta to be common, 400 sine theta. Let's look at another sine theta term, minus 1200. Therefore, 400 minus 1200, that will be equal to minus 800 sine theta. Okay. Here we have cos theta sine theta, and there is again sine theta cos theta. Therefore, minus 400 plus 1200, that will be equal to plus 800 sine theta cos theta. And finally, we have 100 cos theta delta theta. Therefore, plus 100 cos theta, and delta theta will be common. So this will be equal to 0. And we know that since we are giving the virtual displacement, therefore, we can't take delta theta to be 0. Therefore, what is to be 0 is minus 800 sine theta plus 800 sine theta cos theta. This has to be 0. And we can also divide this by dividing by cos theta. We can see that this will be equal to minus 800 tan theta plus 800 sine theta plus 100. This will be equal to 0. So this equation is in the form of 2. Okay, although the variable is only 1, that is theta is the variable, but we have 2 trigonometric functions, therefore that is tan and sine. Therefore, it's not possible to solve by the conventional method. It will be solved by the numerical methods, but we can also solve it on the calculator, on the scientific calculator. It can be solved, and it can be seen that this theta is equal to near about 35 degrees. Okay, it's not possible to solve it by the conventional method. Therefore, we have some numerical methods, or we can also solve it on the scientific calculator. We get that theta is equal to 35 degrees. Okay.